Well, hello, excited to have you back in class, or somewhat at least listening to me here. Today we're going to talk about displacement and how that relates to speed, velocity, and later on acceleration. Our objectives for this is that I want you to be able to differentiate the difference between distance and displacement, calculate velocity, displacement, or time of an object. You'll be able to differentiate the difference between instantaneous velocity and average velocity, and we're going to begin working on a synthesis of a kinematic equation. Distance versus displacement. Well, there's a distinct difference between. Displacement is how far something is relative to its initial position. It can be negative or positive. What I want you to know is that this negative really just tells us the direction of movement. Don't get caught up on the negative. Students let that become an issue, and there's really no reason for it to be. How I'm going to describe displacement is we've got a house that Johnny lives in. We've got a street, and Johnny walks around the street. The length of the street, or the distance of the street, let's say, is 1 mile. Johnny walks all the way around. He gets back to where he started. His distance that he walked is 1 mile, but his displacement is 0. Because if you look at where he is relative to his initial position, he has not moved. He's in the same spot that he was initially. So his displacement is 0. And displacement here is the change in your position, x being position. So your final position minus your initial position. How far an object has moved is its distance. It's always going to be positive. The distance from here, wherever here is, wherever you're sitting, to Kendallville, is a set number. Maybe it's 4 miles. The distance from Kendallville back to where you're sitting wouldn't be negative 4 miles. It's still just 4 miles. That distance is always a positive distance. Speed and velocity. Well, speed equals distance, or displacement, divided by total time. Your speed is your change in position divided by the time. Velocity equals your speed and direction. That's the difference between speed and velocity. For example, you can be going 55 miles an hour down the road, and that's your speed. If you're going 55 miles an hour south, you now have a velocity. Quite often the term velocity is used and speed is all that is really wanted. Or vice versa. Speed is used and what's really wanted is velocity. There's going to be times where you're confused about that. Feel free to ask, and there's never a problem with asking that. Good old-fashioned dirt. Nothing wrong with dirt. Well, in algebra, you had equations. You did a lot of work with distance equals rate times time. Your teacher probably gave this to you as a dirt equation, meaning you had D, and this was in the place of I, and R and T, dirt equation. Distance, rate, and time is what's this relationship. This equation is a relationship between distance, rate, and time. In physics, we use something very similar, but we use displacement, velocity, and time. We replace distance with displacement. How far have you traveled? We take the velocity, or the rate, and call it velocity, and time we leave alone. So in physics, you could say we start to complicate the equation, but we try to be more specific. In actuality is what's happening. Well, during a race on a level ground, Ace runs with an average velocity of 6.02 meters per second to the east. What is Ace's displacement after 137 seconds? One of the things that I want you to get used to doing is making a list of your data. And our list is just simply an example of going through and decoding the information inside the story problem. Because that's what you're going to end up doing a lot here in physics, is having to decode the story problem. It tells us that he has an average velocity of 6.02 meters per second. So his velocity is 6.02 meters per second. It gives me what is his displacement. So his displacement, I don't know. They want to know what is his displacement. So I'm just going to put a little question mark there. And it gives me 137 seconds. Well, now, what I want you to understand is it's no longer am I trying to solve the story problem. I'm just looking at my numbers and solving an equation. If I go back to this dirt equation, and now it's just a matter of plugging in the known information. We find out that the answer is 824.7 meters. All right, meters. Real quick, let's talk about why it's meters. Well, if you look here, the velocity is given to us in meters per second. The time is given to us in seconds. So if I do my dimensionality, what's going to cancel out? The seconds are going to cancel out. We're left with an answer of meters. So my answer would be C. Alright, let's go on here. I've got a problem here for you now to work out using your dirt problem. I want you to go ahead and try working this out. I'm going to go ahead and pause this for a few seconds, and I want to encourage you to try working it out on your own. Well, here I've worked it out for you. The distance equals velocity times time. The velocity is 4.5 meters per second. The time is 22.1 seconds. So when it comes time to find the total distance, or the displacement actually, we multiply it and you get 99.45 meters. Alright, on here, average versus instantaneous. Average is the speed over a long period of time. And what I mean by that is if you're heading south, let's say to Indianapolis, you might have had an average speed of 60 miles per hour. And what that maybe means is you went 240 miles you went 120 miles in maybe 2 hours. So you had an average speed of 60 miles per hour. But during that 2 hours, you might have had several different instantaneous speeds. You could be stopped at a red light. You could have been going slow because you're going down a back road. You could have been going really, really fast because you wanted to get away from an accident. Someone might have been chasing after you. You could have several different instantaneous speeds, even though you had one average speed. What I want you to understand is that instantaneous speed does have a little subscript, and I don't know how often we'll talk about this, but instantaneous speed is quite often, and whether it's instantaneous speed or instantaneous velocity, it's usually shown as this V bar. Alright, well, here's the last thing we're going to go over for today, and that's graphs. I said we'd be doing a lot of work with graphs, and what I want you to understand is that on a distance time graph, a distance time, notice that's two of the things we've really talked about. Distance and displacement are similar, but for this sake, if we have a distance or displacement time graph, the slope of this graph here is going to give us the speed, and that's what I want you to understand, is the slope of this is equal to the speed. So all that work you did in algebra, which you probably didn't care for, was so that you would be able to tell us what exactly, or determine the slope so that we could find speeds, accelerations, and many different things throughout this trimester. So what we're going to spend some time here is finding the speed, and we can find average speed, or we can find instantaneous speed. Average speed would be taking the trend line, because it's an average. So if I look at the very first one, my ordered period would be 3 seconds. It had gone 0.9 meters. So that first ordered pair would be 3 and 0.9. The last ordered pair would be 10, and it looks to me about 2.8, 2.9. So it's going to be 10 and 2.9. Well, when I go to find the slope of this, that's going to be y2 minus y1 over x2 minus x1. So y2 is my second y-coordinate, which is 2.9, minus my first y-coordinate, which is 0.9, divided by x2, which is 10, minus x1, which is 3. So the average speed is the slope of my trend line, because it takes an average of all of the points. To do that, 2.9 minus 0.9 gives me 2. 10 minus 3 gives me 7. 2/7 tells me then that we've got a speed of about 0.28 meters because the y is in meters, and my x is in seconds. Well, what I want to point this out is the slope. This is what you're finding whenever we put that equation into the graph. You're finding the average speed, because the average speed is the trend line here, and this equation deals with the trend line. The average speed is 0.2857 meters per second over the course of this trip. Hey, I hope this is informative. We're going to talk more about the graphs tomorrow. I'll see you on the flip side.